it can majorly be divided into supervised learning, unsupervised learning, and semi-supervised learning. So supervised learning, you basically use data which is labeled, and the labels help to supervise the model training, which leads to better training and a more accurate model. In unsupervised learning, the model does not have any supervision or there's no labels, and the model must discover the patterns and insights in the data by itself. And semi-supervised learning basically tries to combine these two fields, and it tries to combine these two fields and takes advantage of the fact that unlabeled data is rather easy to get and is very abundant. So it tries to take advantage of this unlabeled data and tries to improve the supervised training part. Yeah, so that's the gist of what the three fields are. Now, moving on to the actual topic of the case, is that is supervised learning. So this is a category of machine learning which uses labeled data to train algorithms, which are then used to predict outcomes and recognize patterns. So let's look at some terminologies here. Let's look at what data, label, and model is. Let's start with model. So let's start with the model. Think of the model as a function y equals to f of x, which takes in some input and outputs a corresponding value. Now, in our case, the input to the model, that is x, is the data. This data can be of various modes. It can be textual, pictures, sound, numbers, anything, and it can have any dimension also. So it can be very high dimensional or it can be one dimensional. It can have any number of dimensions, and this would be the x or the input variables, and these are the independent variables for the model. The label, think of it as the y variable. This is the dependent variable and can be in multiple classes or be continuous depending upon the relationship with the data. So let's have a brief look at the training procedure of a supervised learning model. So what you do is you initialize a model. This guy does not know what to do. So he'll just take some input and give out some random output. Now this random output, because it's random, it's almost certain to be wrong. So what you do is you compare it with the actual value, and then you update the model according to the difference over here, whatever you get. So you learn from the mistakes, basically. You learn from whatever the error was in the first prediction. So this model, which was initially very random, is not as random now. So it kind of improves. And you do that for the whole data set, and you do that over the whole data set multiple times until you find that the model performs satisfactorily. This is the brief overview of the model training procedure. Now, the data itself as well can be broken down into three subsets, if you want to call it that way. So we have training data, we have validation data, and we have test data. The training data it's usually 60 to 80% of the data set, and this is the actual data or the information that the model is trained on. So the model only sees this data during training. Validation set is again around 10 to 20% of the original data set, and it is used to monitor the model's performance during training. And it is used to tune hyperparameters. Now, hyperparameters are some parameters which cannot be learned automatically. So you want to keep a track of what is happening during the training, and this validation set is used for that. And the test data, this is like the final exam for the model, or like how good it is and how well it can generalize on unseen data. So this is what the breaking of the data sets, this is how we could break the data sets. Now coming to supervised learning algorithms. Again, supervised learning algorithms can majorly be said to either be regression or classification. In regression, we want to predict an output which belongs to a continuous range of values. So for example, you want to predict the house prices or the salary. So these belong to a continuous range of values and can have an infinite number of possibilities. Whereas in classification, you want to predict a label or a value which belongs to a discrete interval. So maybe you want to classify an email into spam or not spam, or maybe you want to you want to identify dog breeds. So you would have multi-class classification in that case. So the very first, very basic machine learning algorithm that we start with is called linear regression. Now, this algorithm kind of assumes a linear relationship between the dependent variables and the independent variables, and it tries to fit a line, and it tries to obtain the best fit line over the data that we have. So given data points x comma y, where x is say the dependent variable, let's say this is the number of let's say this is the temperature, and y let's say this is amount of ice cream sold. So this would usually, or like intuitively, you'd say this has a linear relationship, or at least a positive relationship, where the higher the temperature, the more ice cream gets sold. So and let's plot the x comma y data points on a graph that we have here. And initially, and let's try to fit a line. So a line y equals to mx plus c, as we know, has two parameters, or in this case, theta 1 plus theta 2x, the slope and the intercept here. So now initially these, you put a line on the graph. This line could be anywhere. It could be like that or like that. It could be anywhere. Uh, yeah, this line has a slope and an intercept. Which are the parameters that define this line? So we basically want to optimize these parameters or obtain such values of the parameters such that we obtain a line which fits this graph very well. So now also let's call the given labels or the given amount of ice cream sold as yi, and let's call uh, the output of the model or the output on the line of the y part. This is the prediction of the model. So this is obviously going to be wrong. You can't have a line which squiggles enough to go through all these data points, and if it does, that's not a very good model. So yeah, we want a model to generalize well. So this is y is the prediction and it's the point on the line, and yi is the original value, which is not a point on the line, or it could also be a point on the. So these would be off by some amount, and they would have some amount of error. So we want a way to quantify this error. To quantify how wrong the model's prediction is, we use something called loss functions. So I have basically said what loss functions do. They quantify how wrong the model's prediction is, and this would further help into optimizing the model. So we use some loss functions like mean absolute error, mean squared error, or root mean squared error. They are all kind of taking the error and then taking an average over the error, or squaring the error and then taking an average. So let's take a look at how we can optimize the linear regression model. Note here we're using the mean squared error loss function. So yeah, let's say y or h of x, the function, is theta naught plus theta 1x, some mx plus c line, which has a slope and an intercept. Now initially, this is not a good line. So we want to optimize the parameters. Now theta naught and theta 1 are the parameters that we want to learn, the slope and the intercept. So this line, you would put a line initially, and you'd get some outputs on this line, points on the line corresponding to the inputs, and you would calculate the cost. Now, once you calculate the cost, you have an idea of how off your model is. So if you look at it here, this particular cost function, the mean squared error, and if you substitute h of x over here with theta naught plus theta 1x, you get that the cost with respect to either theta naught or theta 1, if you draw a graph, would be a quadratic relation. So it would look something like this. And depending on whatever random value your weight, that is theta naught or theta 1, has on the x axis, on the weight axis, you would get a corresponding value of the cost. Now our goal is to get such a value of the weight, that is a value on the x-axis, such that the cost is minimum. So to do this, we use something called gradient descent. Uh, so we calculate the gradient of the cost function, which is nothing but the partial derivative with respect to whichever parameter we're optimizing. So if you were to do the math and calculate the gradient for theta naught, which was our intercept, you would get this. And if you were to calculate the gradient of theta 1, you would get this. Now, this partial derivative here is nothing but the tangent to this slope. It's nothing but the slope or the tangent over here to this point on the graph. And if we take a direction negative to that of the tangent, we actually get the direction in which we should move to reach the optimal or the global minimum for the cost. So this is why we use the gradient of the cost here. And once we know which direction to move in, we can decide on how much or how big of a step we want to take, and that is governed by alpha, which is the learning rate. So if you have a higher value of alpha, you take bigger steps, and if you have a lower value of alpha, you'll take smaller and smaller steps. Yeah, so that's for linear regression. I will hand it over to Alan to continue from here.
So hello guys, I'll continue from logistic regression. Just confirm if you can see my screen. One sec. Hello, so can you see my screen? Akash, could you just tell if you could hear my voice also?
Yeah, it's visible and you're audible.
So logistic regression is another form of supervised learning which deals with classification. We saw those two things, regression and classification. So this deals with classification. But then the name is still logistic regression. You'll see why it's called regression still when you later on. So let's say in classification thing is in regression we had values, we had continuous values. The output y was continuous. You could like on this line you could for some x you would get some continuous value of y. And but in logistic regression what you want is discrete values. You want a yes or a no. So let's say you are applying for a loan. You want to know whether you will get accepted for the loan or not. So we need an yes or a no kind of answer. So if you do our linear regression on this is the same exact same steps which we for linear regression on this kind of data, where it's just y equal to 1 and y equal to 0 are the only outputs, actual outputs we have. Your graph, your line, the best fit line you would get would look something like this. But then the issue is for a certain x value, like let's somewhere over here, the y value would be like near 0.5. So you're not really sure whether it's a yes or a no. It's like it's not 100% sure. So for that, we need to change the line into a curve, a squiggly curve like this. And here now, if the same value over here, you take some value of some like for the same x value, the y value this curve outputs is near 0, and that's like it won't be exactly 0, it'll not be exactly 1 also, but it'll be more, it's better than what we would have gotten using this line. So that's what logistic regression is trying to do in essence, and we'll see how it does this, how this curve and what this curve is called also. So first of all, this curve, this s shaped curve is called a sigmoid graph, a sigmoid function. This is the function f of x equal to 1 by 1 plus e raised to minus x. And this is how this function looks. You'll see this function a lot in other machine learning applications too. So I will see how we convert that straight line we had over here to this sigmoid function. So initially, this was the equation for our straight line y equal to mx plus c. It's the same thing, just the variables are a bit changed. So instead of theta naught and theta 1 is beta naught and beta 1, but it's the same thing essentially. This y equal to mx, we put it into the sigmoid function. Sigma of z just represents the sigmoid function. It's just uh, you'll see in the end over here what the you're just plugging the value of y equal to mx, the y value into e raised to like 1 by 1 plus e raised to minus x. Instead of x, you're putting the output of linear regressions line, and this would be our new curve. This is a like curve we're trying to optimize and fit to our data. And how we do this? I mean, we need a cost function obviously for this to know how wrong we are. Same as in linear regression, we had mean square error or root mean square error. So here we have a slightly different cost function, and the reason for why we are not using mean square error is because mean square error versus parameters would give a slightly different, it will give a more bumpy graph. It wouldn't exactly be a quadratic graph. So that's why we are using this cost function, which is minus log of h of theta x is just y. So minus log or like our output y. So it's just minus log of y if the actual value of y is 1, and minus log of 1 minus y if the actual value of y is 0. And so this is how the cost function would versus the versus y would look like for this new cost function. But the thing is, we can't exactly use this conditional function. We need to convert it to a singular function so that it's differentiable. And for that, we have this simplified cost function. And now it does look a bit complex, but it's actually very easy, simple. If you look over here, there's a y value over here, and there's a 1 minus y value over here. And these are actual output values. So it's either 1 or 0. So this, if it's 1, or if y equal to 1, here if you put y equal to 1, this 1 minus y term would get cancelled out, and here it will be y equal to 1. So your final answer would just be log of h of x. And if you put y equal to 0, your final answer, I mean, this part would just get cancelled out, and your final answer would just be log of 1 minus h of x. So it's just the same function over here. It's just simplified into a singular function, so that is easily differentiable. And now we do the same step we did in linear regression, which is gradient descent. We differentiate it with respect to every parameter theta and subtract it times learning rate, and we repeat it for multiple steps, and we will have an optimal curve that fits the data. So this differentiation of the cost function versus theta, if you do the math, actually it would look something similar to this if you differentiate this function over here, and that's mostly logistic regression. Now we'll talk about support vector machines, SVMs. It's also another way of classification itself, just a slightly different approach to it. So let's say you have some kind of data like this, where x1 and x2 are features. Let's say x, again the same bank loan accepted example. Let's say x2 is how much balance you have in your bank, and x1 is how old you are, and you need to predict whether you are eligible for a loan or not. So let's say these blue points are you are eligible, and these red points are you're not eligible. So like if you just think it logically, like a normal person, if you were to just draw this graph and by hand, if you wanted to figure out a line or some way of classifying these two things, what you would do is just draw a line between them. So anything above this line is accepted, anything below this line is not accepted, and that seems simple. And it's just and now we'll and about this line is called a hyperplane. So the mathematical definition for it is a flat affine subspace of a higher dimensional subspace. Now I'll just simplify it a bit. It's just some kind of boundary that splits the actual space into two parts. So let's say your space is this 2D graph, and this line is your hyperplane, which splits this 2D graph into two parts. And this can be done for any dimension of any dimensional space. So you have an n-dimensional space, you'll have an n-1 dimension hyperplane. So like let's say you have a 3D graph, then you'll have a 2D plane as a hyperplane. If you have a 2D graph such as this, you'll have a 1D line as a hyperplane. And if you have a 1D line, like let's say your space is just a line, then a point would be your hyperplane. Anything left of the point would be accepted, like so one class, and the anything right of the point would be your other class. And now let's talk about what support vectors and what SVMs are. So the main thing about SVMs is the support vectors. So we'll talk about support vectors and how we find them and how it helps in defining this hyperplane. So before you talk about the math and all these notations you see on the screen, let's just talk about the hyperplane over here, this red line, and these 3 points you see over here, the blue point and the two blue points and the green point, that's your support vectors. And let's talk what a margin is. A margin is just the distance from this dotted line to this red hyperplane. And yeah, that's your margin. So now we'll talk about how we find these support vectors and how these support vectors will in turn help us find the hyperplane. Before that, oh yeah, something about the mathematical notation you're seeing over here. If you haven't like studied linear algebra, it might be new to you. But then if I'll just give an analogy of how it's similar to something you studied in 11th and 12th. So if you had like equation of a plane or something 3D in 3D space, you would have r dot n cap equal to d. If you remember your your 11th and 12th, this is similar to that, not exactly, but w transpose x plus b equal to 0 is just the general equation of a hyperplane. And so w is just a vector that is perpendicular to the hyperplane, and uh, b is just called the offset. And for any value of x which it satisfies, this equation satisfies equal to 0, uh, that point would be a point on the hyperplane. And more interestingly, any point not on the hyperplane, you some x value you give, and you will get either something greater than 0 or less than 0. And that helps us classifying. So anything greater than 0 is one class, and anything less than 0 would be another class for you. And so that's what you're saying, this wx minus b equal to 0 here, and then this wx minus b equal to 1 and wx minus b equal to minus 1 is just two extra planes defined by the support vectors. And the difference, like the distance or the margin distance, if you do the math, 2 by mod of w, and that is important. We'll see how once it. It's mostly important for our cost function. So before exactly talking about this equation over here, which is mod of w by 2 phi summation each, looks kind of not like clear right now or not simple. We'll talk about it in logically. What our cost function is essentially trying to do is just to maximize this margin. So margin
Why
already
you not
defined this gap, and we need to just try and maximize it to get an optimal line that splits the splits the data into two classes. And what outliers are is this blue dot over here. So this outliers exist in data. Normally it just happens and it's just random chance, and you can't really do much about it. If you were to try and include this blue dot into our other blue dots, then you would misclassify some of the green dots, and that would be bad. So we can ignore some of these outliers as long as we get a good enough result. We can't completely avoid every outlier, but we can try and avoid some of the outliers and still get a good enough classification. So this function, now if you think about it, we have to maximize the margin, and the margin is 2 by mod of w. So you just minimize w by 2, and that would maximize the margin in turn. And eta is defined as the distance of the outlier, like the incorrect data point or the outlier from the margin. So it's just this distance from this dotted line to this blue point. And so that is your eta, and ci is just a hyperparameter which is similar to alpha. Here it just says how much points should we deduct for an outlier. So like how less, or like if you increase c, it would cost you more, and you would try to minimize outliers. If you decrease c, you'll give a more lenient cutoff for outliers. You would let more outliers be there, and that is your cost function. Now this cost function is what helps us find our support vectors. So these 3 points are found using that cost function. So if you remember again in engineering mathematics 1, we had a topic called Lagrange multipliers. So we use that to, if you don't remember, it's just something that we use to minimize a function given some constraints, or minimize or maximize a function given some constraints. So we use that, and we could find the support vectors easily. I won't go into detail of that math now, but then using that, you could find these support vectors, and using these support vectors, you can find the hyperplane easily. And yeah, that's mostly of SVM, but now let's talk about a different kind of data for SVM itself. Like let's say your data looks like this. So now if you try and draw a line to split the data into two parts, it's not easy. You can't exactly draw a line anywhere such that the red is separated from the green, you would always have some red mixed in with the green and all. So for that, there is two things. One way we could do solve this issue is by changing the axes. So you have x1 and x2. Instead of that, you could take r and theta, the radius and the angle theta. So the same graph, instead of x and y values or x1 x2 values, if you convert it to r and theta values, it will look like this. So like r and theta around a point. So let's say around this point over here. So R value of the green points would be high and the R value of red points would be less, because it's you can see it from the graph itself. So based on that, you would have a graph like this, and now we could easily uh, split it into two parts. But the thing is, this is not easily done. I mean, now we just saw the data and we could do it, but we're talking about higher dimensional data and like more features, not two features. We'll have like 10, 20 features, and it's not easy to do this for 10 and 20 features. So people came up with a better approach. It's called kernel functions. So in simple terms, what kernel functions do is it maps it maps something from a smaller dimension space to a higher dimension space. So let's say you have 20 features, it will map it to 40 features or so, or two features over here, it will map it to three features, and so on. So that's what a kernel function is trying to do. So why is it useful? Is because of this. You see over here, once we converted this 2D graph to a 3D graph, you have the data look like this, and now we can draw a hyperplane which cuts the red data points and the green data points separately. And this is what a kernel function does. Another simple example is like you take this line and you just put y, and now you can't really, a hyperplane over here would be a point, and you can't really place a point anywhere to split this data. But if you were to do y equal to x square, now the data would look like this, and you can easily draw a line that splits this data into two parts. But the thing is, doing this conversion of like 2D to 3D or 1D to 2D, and normally we'll have 20 dimensions to 30 dimensions or so, or even higher. It's not, and then calculating this line is not easy. It takes a lot of computation, and so that's why we came up with something called the kernel trick. And we can do it for these kernels, like only certain kernel functions. One is called the polynomial kernel, and another is called the radial basis function kernel. There are some other ones too, but these are like some of the common popular ones. So the polynomial kernel is this k of xy equal to x transpose y plus 1 the whole raised to d. So this would give us the distance or the similarity between two data points in a higher dimension. Like this would calculate that value directly for us rather than manually converting x to a higher dimension, y to a higher dimension, and then calculating the distance or that similarity. This would do it directly for us, and this d or this gamma over here is hyperparameters which you can tune during using your validation set. And yeah, this is mostly for SVMs. And now decision trees, Akash will continue.
Hello. Uh, any doubts if you guys have, you can drop them in the chat for now, or otherwise after the session you can also unmute and we can take doubts. Yeah. So continuing with decision trees. Now decision trees is another supervised learning algorithm which can be used for both classification and regression. So what a decision tree does is it basically splits your data at various nodes in the tree and tries to group kind of similar data together uh, at each split. So this is the basic idea of a decision tree. So it splits nodes into subnodes, and then those splits which maximize purity are kept. So we'll come to purity in a moment. Yeah. So this is what a simple decision tree which classifies animals would look like. So you have the root, which is basically the full data, and then let's say you try to break it on the height of the animal. So is it short or tall? and then maybe you can then you break it on the sound that the animal makes, or maybe the length of its neck, nose, or where it resides. So at every split, you calculate something called the purity, or sorry, you calculate something called the impurity of the split. So what is oh, and before, sorry, my bad. So let's restart. So you have a decision tree, and then this decision tree, what you're doing is you're essentially taking decisions at every node, and you're splitting the data according to whatever decision you make here. So if you were to split these animals based on their height, so you'd get short and tall, and then you could further classify them or break them or split them into whatever sound they make and whatever kind of neck they have or nose or their habitat. And based on these conditions, you might uh, end up with whatever kind of animal they are. Now, these do seem like just a bunch of if else statements, but then the machine learning part here is to kind of identify what the ideal if else condition would be. Now, coming to some terminologies, we can have three types of nodes in a decision tree. You can have a root node, a decision node, and a leaf node. Now, again, a leaf node is basically where further splitting is not possible. This most likely happens when you have a final outcome or a final classification, and because they're final, you can also call them terminal nodes. Decision nodes, again, decision nodes are the nodes where you're actually taking decisions. So wherever you're kind of splitting your data, and the root node is the initial node at the beginning of the decision tree, where you start actually dividing the population or the data set. Now let's come to what purity or impurity is. Like we said that our goal in the decision tree is to create pure splits at the end. So what does purity or impurity mean? So let's say you have this box of positives and negatives, and we let's look at the left side split first. So you see that here the number of positives and the negatives in the left side are kind of similar, and again the number of positive and negatives in the right hand split also are similar. But if you look at the one which is captioned as pure split itself, you see that the number of positives on the left side are kind of more, and the number of negatives on the right side are like significantly more. So you can kind of tell which side is the positive side and which side is the negative side. So this is what we mean by a pure split, that the kind of data present in this split should be similar. Now, it comes from the word itself. So when you say you want to measure purity or impurity, you can use some measures of similarity or some measures of impurity as you call them here. So these are some very popular measures of impurity that we use. So this is the Gini index and this is entropy. These basically come from how likely an event is supposed to happen. And for more math, we'll link resources in the at the end of the PPT. And yeah, we'll be sharing the PPT with you guys if this wasn't mentioned already. So so basically when you choose a split, so how do you know if splitting on the height is the best decision to make over here? Why didn't we split on the kind of noise that the animal makes here? So to do that, what essentially happens is the computer or the model actually tries out all the splits and then decides which split to take here based on something called the information gain. The information gain is basically the entropy, or I'll call it impurity here. You could use any other measure of impurity over here. The impurity of the parent minus the impurity minus the weighted sum of the impurity of the children. So over here, the weighted sum would be 1, 2, 3, 4. So basically, the proportion of the number of entries of the parent, you take the proportion and you multiply that to the impurity values of each split here. So that is what we mean by the weighted sum. So yeah, you do that, and then you get the information gain. So let's say the parent was very much impure, and the child, the whatever split you've created, are pure. So this kind of represents an ideal scenario where the information gain is going to be high. So this is impure, so this has a high value, whereas the entropy or the impurity in the splits are is less because you created pure splits. So in this case, the information gain will be high, and therefore this would be a more ideal split to make. So let's look at an example. Let's say you have a data set of fruits based on their shape, color, and taste, and you want to classify them into oranges or mangoes. So what you do first is you calculate the entropy at the root itself. So what is the entropy in this stage itself? Now this is basically the formula of entropy that we saw here, just a summation over each class ka log, probability times log of the probability. So this is what we've done here, and P of M represents probability of mangoes and O represents probability of oranges. Now since these are just two classes, you can replace PO by 1 minus PM and it would stay the same thing. So we have defined entropy as kind of a function of the probability of finding mangoes here. Now in this case, the probability of finding a mango is 5 by 10. So we put that value and we calculate the entropy at the root, and you get a value of 1. Right. So now let's try to split based on the shape of the fruit that we encounter. So let's say we have split on the shape and we decide if it's round, we put it to the left. If it's oval, we put it to the right. Now, now we want to calculate the information gain we get the information gain we found based on this split here to see if this is a good split or not. So to do that, again, we'll calculate the entropy for this split and then the one for this split and then take a weighted sum of that. So we calculate similarly the entropy for round. So here the probability of mango is 0.2. So you put that in this same formula and you'll get a value. Similarly, for the oval split, you get probability of mango is 0.8. You put that same thing in the formula and you get an entropy value. So you get the entropy for round and oval was 0.72 each. And then you weight them and add them together to get the total entropy over here. And you find that it is 0.72. Now, to calculate the information gain, you simply subtract the entropy over in this state uh, from the root. So you get an information gain of 0.28. Now, this is the information gain that we obtained if we split the data based on its shape. Now, what if we split it on, let's say, the color or the taste? We would simply do the same procedure, calculate the information gain over here, and then decide, and then whichever one has the highest information gain, we start splitting on that on that feature of the data. So if you were to do that, you would get the following results. For shape, you would get an information gain of 0.28 as we have seen. For taste, you would only get an information gain of 0.04, while for color, you would get an information gain of 0.13. So in this case, the highest information gain is obtained by splitting on the shape of the fruit that you have. So we go ahead and split on this. Now, once we do this, you have to repeat this procedure for every subtree that you encounter. So what I mean by a subtree is basically this. So once you have split it over one feature, what you have here is kind of another root node itself, and you want to classify until you find very pure samples here, or you want to classify until you have pure samples over there, which is containing only of one class, or when you have violated the maximum depth of the tree. Now, this is a hyperparameter that you can set in advance. So how decision trees work internally is recursively. So if you have a very large data set or a very complicated data set, these trees can go almost infinitely deep. Like it wouldn't be infinite, but it'll be very, very deep. And that would take a lot of time to actually train. So you can set a maximum depth to these trees. So if it goes below that, then you can like stop over there. Or when the improvement in information gain is below the threshold value. So let's say you made some splits, you made a split based on shape and color, and then you see that you get some results. Let's say you get an accuracy of 90%, and then you split it again based on taste, and you get an accuracy of based on, let's say, this information gain value. Let's say you get an accuracy of 91%. So you say that the time we wasted in splitting the data again on taste was not worth the increase in performance that we found. So you can just stop if the information gain is below a certain threshold value. And again, the number of data points in a node. So let's say you end over here itself. Let's say you end at some node where there's only one orange, and the other four oranges are here, and other five mangoes are in some other split. So this particular split over here, which has only one orange, would be reliable because unreliable, sorry, because the sample that this guy has seen is only of one. So you can't really rely on this. So this is what you mean by the number of data points in a node. So you can set a threshold value for this as well. All these three, the maximum depth, the threshold for information gain, and the threshold for number of data points in a node, are all hyperparameters that can be set by the user or the programmer itself. So this is the final decision tree that you get. This was, you can actually view this in TensorFlow, I think, and this is the final decision tree that you get. And you see how in the root nodes, they're very, like, most of them are very pure samples. So you can't. I think this one stopped only because you can't split it further. So yeah, you see how the entropy here is 0 0 0, and whatever, so let's say you have a new fruit now and comes down to this box. Now we would call, so whatever fruits are here, oranges or mangoes, this new fruit would also be called an orange or a mango based on whatever box it goes to. Yeah, this was decision tree for classification. Now, if you talk about regression, you can again use decision trees to solve regression problems, except the purity measure, or kind of the similarity measure you use now, is usually the variance of the sample. So you take the variance and you take the average variance. Uh, yeah, and that would be the measure of similarity for that, for the regression problems. And let's say you have some three samples here, and let's say you have some three, let's say, persons in this box, and they have some height. Obviously every person will have a height. So, and a new person comes in and again falls into this box. So the height of this new person would be set to the average of the heights in this box. So this is how a decision tree would also work for a regression problem. Yeah, so that's about it from our side for this session. We have covered a lot of stuff, really, in supervised learning. We started with linear regression, logistic regression, and we've covered techniques like SVMs and decision trees. So yeah, that's it from our side. We've linked some resources here in the PPT, and we'll be sharing the PPT with you. So yeah, thank you everyone. If you have any doubts, you can ask off in the chat, or I think you can even unmute and ask if that is allowed right now. So if anyone has any doubts, I think you can just put it off in the chat. We'll be happy to help. And if you don't have doubts, you can leave the meeting. That's it from our side.
Uh, can you explain once more the decision tree for regression?
Yeah, just a minute. So for regression, let me share my slides. So so let's say instead of having oranges or mangoes, let's say you had price of the fruit here. So some 100 rupees, 110 rupees, 150, 200, 300 rupees. So in this case, you can't really group the labels together, right? So you have a continuous range of values. But even in this case, what you can do is you can start splitting them based on their shape. So let's say you split them on their shape, and the values that you get here just so happen to be that they're less than 200 rupees worth of fruits worth less than 200 rupees. And the fruits that you get here are fruits that are more than 200 rupees in worth. And you just essentially repeat the same process. But the problem here is, how do you calculate the purity or impurity of the sample over here? To do that, you just use the variance, you just use the variance over here. So let's say you have a sample, and the values in that range from, let's say, 0 to 1000. This would have some amount of variance. But and then you just take a subset of that sample which has a lesser range, and depending on whatever values it has, you get another value of variance. So this now is your measure of impurity that you use. So over here, the parent would have some measure of variance. That would be the impurity of the parent. And you would get some measure of impurity for the splits that you create. So you essentially replace entropy here by the variance of the samples that you obtain after splitting the data. So yeah, that's essentially the difference between decision trees for regression and decision trees for classification. And when it comes to making the final prediction, so in classification, let's say you have a bucket with 6 oranges and 4 mangoes, and if some other fruit just happens to land in this bucket, because this bucket has a majority number of oranges, you would label this new fruit as an orange. But when it comes to regression, let's say you have a fruit and it comes to this bucket, and this bucket has fruits which cost 10 rupees, 20 rupees, and 30 rupees. It has three fruits which cost 10, 20, and 30 rupees each. So the value of this new fruit would happen to be the average of the values in this bucket. So that is the idea essentially stays the same. For more details, you can check out a video we've linked over here. Yeah, so I hope that clears your question. Do you have anything else to ask?
No, I got it. Thank you.
You're welcome.